Okay, today we're going to be deriving the molecular orbitals for the diborane molecule. Last time we did plain old borane, BH3, and we found that one of the atomic orbitals on boron was not even used for any bonding. It had an empty pz orbital and could not achieve an octet. And so we discussed that is the basis for the dimerization reaction that leads to the diborane molecule, and we're interested to observe the form of the molecular orbitals to see if in the diborane molecule all of the valence electrons and all of the valence atomic orbitals of boron actually are able now to become involved in bonding interactions. So this is diborane. And this belongs to the D2H point group, and that's actually the same point group as ethylene. So many of the conclusions that we'll draw about the form of the molecular orbitals for diborane could also probably apply to the ethylene molecule, and that would be something that you could investigate separately. As we go through the problem, I'll draw the skeletal connectivity of diborane in a couple of different orientations. This is the first way to do it. In this particular way of drawing the skeletal structure, we have the bridging hydrogens and the boron atoms in the plane of the page. And in this orientation, we're going to make vertical the x-axis, and the diboron axis will be our z-axis. And if I rotate that structure about the z-axis by 90 degrees, then I'll draw the skeletal connectivity this way, with the 4 terminal hydrogens in the plane of the board and the 2 boron atoms also in the plane of the board. And now when I draw it that way, we have our y-axis in the plane of the page pointing up, and our z-axis in the plane of the page pointing to the right. So that's how we'll see it as we go through this problem. For your reference, if you don't have handy the D2H character table, in this coordinate system, we'll recognize that something with the symmetry of a px orbital will belong to the B3U, irreducible representation of D2H. Something with the symmetry of a py orbital will belong to the B2U, irreducible representation, and something with the symmetry of a pz orbital will belong to the B1U representation. So that's just a little bit of the D2H character table reproduced here for our convenience. And I'm going to use the same strategy to develop these orbitals as I did with the borane molecule. And that is to say that I will consider the boron valence orbitals. Boron has 4 valence atomic orbitals, an s and 3 p orbitals. And I'll start with the boron valence orbitals, and then we'll see how to add in hydrogen contributions so as to maximize the bonding in the system. And so if I start out by considering the boron 2s orbital here, by symmetry, if I put in the s orbital on the left boron, I'm going to also have to put it in on the right boron, either with positive or negative phase, depending on which irreducible representation of the point group this belongs to. I'll start out with the same phase, and so if the borons were pretty close together, they're kind of a little bit farther apart because they have bridging hydrogens, so they're not in the distance that you would normally expect for a boron-boron single bond. They're kind of stretched apart. It's like a stretched ethylene, but with bridging hydrogens on top and on bottom. Another thing I should point out is that when we draw the diborane molecule like this, we have 1, 2, 3, 4, 5, 6, 7, 8 lines between nuclei, We normally think those lines correspond to 2 center 2 electron bonds, but we have 8 lines here. That would be 16 electrons, and we only have 12 valence electrons in this system. Let me just make a note of that. This is 12 valence electrons in this system. And that's important to keep in mind because we can only get 6 electron pairs into molecular orbitals since we only have 12 valence electrons available to play with. Now, I want to start out by trying to make an orbital that will be everywhere bonding, and so I'll put in the hydrogen contributions like this with the same sign on all 4 of the terminal hydrogens, because certainly those all look the same from the perspective of these boron s orbitals, and so all of them could bond equally in this molecular orbital. And also, the hydrogens above and below the plane, one here above the plane and one back behind the plane, can come into this orbital with the same sign, positive everywhere, and in so doing, we've written down the basis for an orbital belonging to the totally symmetric representation of D2H, and that is an A sub G molecular orbital. And G, remember, means that an orbital is Gerada or symmetric with respect to inversion. So if you start out somewhere on the orbital and you see a positive sign, if you go to the opposite, go through the middle and to the opposite part of the orbital, you should find the same sign. So that's symmetric with respect to inversion or Gerada. These orbitals over here that are like P-orbitals are going to carry a U for ungerada, and that's a designation that we give to orbitals that are anti-symmetric with respect to inversion. And so, next, let's do the other possibility for the boron s orbitals. If I take the first one and make it positive, and take the next one and use opposite phase, I'll actually shade this one negative on the left, because we're going to find out that this orbital will have symmetry properties reminiscent of a PZ orbital, and I like to have positive phase along positive Z and negative phase along negative Z. And now, let's complete this with maximum bonding to the hydrogens. We'll draw in the 4 terminal hydrogens, and we'll see that we can make nice boron-hydrogen bonding interactions on the left-hand side and on the right-hand side, though this orbital does introduce an internuclear node here that is indicative of boron-boron antibonding character, but there's lots of boron-hydrogen bonding character in order to make this a net bonding molecular orbital. And additionally, we can ask, will the bridging hydrogens be able to contribute at all to this molecular orbital? And the answer is no, because the bridging hydrogens actually lie on this nodal surface between the borons, and they're bisected by it. And this is similar to the case where you have a hydrogen s orbital adjacent to a p orbital, where there's no net interaction because the hydrogen lies in the nodal plane. And so this molecular orbital looks uniquely like this, and it carries a B1U subscript because it has the symmetry properties of a p orbital. Okay, we generated a couple of molecular orbitals that are bonding molecular orbitals by starting with the boron s orbitals, and next we'll go ahead and start looking at orbitals that we can generate using the p orbitals of the system. And I'm going to, for that, use this other way of orienting the system, and I'll start with the px. I'll start with the px orbitals of the borons to build this molecular orbital. Okay, so this orientation puts the x vector straight up, and so I'll draw a nice p orbital here on this boron. It's a px orbital on the left-hand boron, and I'll draw a px orbital on the right-hand boron. And so if these two boron centers were close enough together, these orbitals could overlap on top and on bottom and form a boron-boron pi bond. But this system has, as I mentioned before, kind of a stretched boron-boron pi bond. And so what we'll get when we add in the hydrogen contributions on top and on bottom is that the hydrogen s orbitals bond to the top lobe up here and the bottom lobes down here. And because the four terminal hydrogens lie right in the YZ plane, which is a nodal plane for a px orbital, those four terminal hydrogens can't contribute at all to this molecular orbital. So if we run a molecular orbital calculation, we should really find a molecular orbital that looks very much like this. And because it has the symmetry of a p orbital, a px orbital, it'll carry a B3U subscript. Okay, next we'll go to the py orbitals and generate another bonding molecular orbital. My goal here really is to draw 6 bonding molecular orbitals to accommodate the 6 electron pairs that we have in this 12 valence electron system. So there's a py orbital because I've reoriented the molecule such that the YZ plane of the molecule now is in the plane of the board, and I'll make this an orbital that would be boron-boron pi bonding if the borons were close enough together, pi bonding in the plane of the same plane as those four terminal hydrogens. And so now we can have boron-hydrogen bonding character kind of oblique because these p orbitals aren't pointing their lobes directly at the hydrogen. It's a bit off axis, but we can still make nice bonding interactions with those four hydrogens that are in the YZ plane, like that. So we have 4 nice boron-hydrogen bonding interactions. And what about the hydrogens that are on the x-axis? Can they contribute at all to this molecular orbital? The answer is no, because they lie in the nodal plane of these two py orbitals. And so they can't bond to those py orbitals at all, so they don't appear in this molecular orbital. And this has the symmetry of a py orbital, so this carries a B2U subscript. And so that's bonding molecular orbital number 4. And let's continue on here and get to the next one. We've done a bonding MO based on the boron px's and py's. What about a bonding orbital based on the boron pz's? I'll draw a pz orbital like this. And in order to give it the maximum amount of bonding character, I'm going to invert the phase of the left boron p orbital, pz orbital, relative to the right one, so that we can get boron-boron bonding character here in the center. My goal is to generate molecular orbitals that maximize the bonding character so that I can find out what the bonding character is, or what the symmetry properties are for all the most strongly bonding molecular orbitals in this whole system. And so once I've generated this orbital, I can see that it is possible to get contributions from the terminal hydrogens as follows. This again is kind of an oblique off-axis interaction between the hydrogens and the pz orbital lobes, and those all come in on the left and the right with positive sign. And then I see that it is possible for the terminal hydrogens, the bridging hydrogens also to contribute to this molecular orbital, so I'll draw them in. There's one right there, and one in the back with negative sign. So this will be a molecular orbital with 2 nodes, and those nodes are not internuclear nodes, they're just natural nodes coming from these 2 boron p orbitals, so it's plus, minus, plus in this molecular orbital. And if you carry out all of the operations of the D2H point group on this picture, you'll see that you'll always get back a character of 1, because this orbital can serve as a basis for the AG irreducible representation. And it's symmetric with respect to inversion. All of these 3 orbitals are anti-symmetric with respect to inversion. but this one is symmetric with respect to inversion, just like the first one that we made that was based on the boron in phase 2 s orbitals. And so because that earlier one and this one are of the same symmetry, it's possible that they may mix to some extent when the final molecular orbitals are formed. But this is a good bet that we're going to see a very low-lying molecular orbital with the same sign everywhere, and we're going to see another Ag orbital with these properties of plus, minus, plus. And after you're done viewing this video, you should go back and look at the diborane molecular orbitals in the online applet that we provide so that you can confirm that we've actually done a good job of predicting the phase properties and symmetry properties of the diborane molecular orbitals. Okay, then, having done that, we've got 5 now of our 6 bonding molecular orbitals, and we need to get one more. And we're going to do this similar to what we did for this B1U. Namely, we're going to take either the PX or the PY or the PZ, and instead of using a bonding combination like we did for this one, B3U, B2U, and this Ag orbital, we're going to go ahead and use an antibonding combination. And because we're using an antibonding combination, I think you'll be able to convince yourself that we can't use the PX orbitals, because if we did that, then we would have plus here, we'd have minus here and plus here, and these 2 hydrogens now would be on a node of that orbital. We're looking for a pi star orbital that we can make, where we can make bonds to hydrogen to stabilize this orbital and convert it into a net bonding molecular orbital. And so we can't do it with the PXs I've submitted, and we could do it with the PZs, but then we'd have a really strong sigma antibonding interaction in the center, and it's less unfavorable to have a pi antibond than a sigma antibond for reasons of direct overlap. And so we've ruled out the X's and the Z's, and so we'll choose the PY's to be our antibonding, a boron-boron pi antibonding orbital that will base this bonding molecular orbital on. So these are in the same plane as the 4 terminal hydrogens, and we'll do the shading like this. This generates our boron-boron internuclear node antibonding character just between the borons. And then we notice that we can't have any contributions from the bridging hydrogens due to a nodal plane right here, but we can make nice boron-hydrogen bonds using the terminal hydrogens. Like that. And having shaded it in, it's actually pretty interesting, because we'll see that the phase properties go in alternating in the 4 quadrants. We have plus in the upper right, minus in the lower right, plus in the lower left, and minus in the top right, in the top left. Sorry. And those properties, interestingly enough, have the same symmetry properties as a d orbital if it were based at the center. And as you learn more about d orbitals, you'll see that this actually has the same symmetry properties as a d sub yz orbital, because this is the y-axis and the z-axis, and we go plus minus around the quadrants, and that's what the nodal properties do for a dyz orbital. And so we can look in the character table and see where we find the yz function, and it turns out that that's actually a b sub 3g. This is Gerada. S orbitals are Gerada and d orbitals are Gerada, where p orbitals are ungerada. And so now what we've done is we've actually managed to find bonding molecular orbitals by sequentially going through the boron valence orbitals, starting with the s orbitals in phase and out of phase, and then the p orbitals in phase, in phase, in phase, and one out of phase. And at that point, we have bonding molecular orbitals in which to place all of the valence electrons of this system. So we can draw a qualitative energy level diagram. And because in the D2H point group, each of the representations is singly degenerate, we know that each of the orbitals will have different energies. And so we go 1, 2, 3, 4, 5, 6, and then we expect to encounter our homoluminal gap, HLG. And then at higher energies, we're going to find all the antibonding molecular orbitals that correspond to these bonding orbitals. And in fact, if you are interested to know how many virtual orbitals there are, virtual meaning unfilled orbitals, let's fill these ones in with our 6 electron pairs for this 12 valence electron system. We have 4 valence orbitals for each boron, and that's 8, and then we have 6 more for each of the 1s orbitals from the hydrogens. So we have a total of 14 electrons in this system. And so in addition to these 6 filled molecular orbitals, we must have 1, 2, 3, 4, 5, 6, 7, 8 empty orbitals in this system, taking the assumption that the number of molecular orbitals equals the number of atomic orbitals. And if we do an MO calculation, and you can look at the online applet showing the 3-dimensional molecular orbitals, the energies of these orbitals actually does go, according to the calculation, in the same sequence that we generated. So if the lowest lying one is an AG, all these up here are star antibonding molecular orbitals. And then, so it goes AG, and then B1U, and then B3U, and then B2U, and then the second AG, that's the one that has plus, minus, plus, and then the B3G. So the one that looks like a d orbital in terms of nodal characteristics is actually our highest occupied molecular orbital. So just by reference to the character table and by constructing bonding molecular orbitals, we could actually do a really good job of qualitatively predicting the molecular orbital energy level diagram for this system. One thing I will say, by way of justifying the energy of these orbitals, is that the lowest 2 here are ones that are based on a lot of boron 2s character. And the boron 2s character, boron 2s orbital is much lower in energy than the boron 2p orbitals upon which these orbitals are based. So these orbitals are based on boron 2p. And then you might have intuitively felt that the last orbital here was the highest lying because it had an antibonding node between the 2 boron atoms, justifying the prediction that it would be based on the HOMO. Once we've decided that the ones with a lot of boron 2s content would be pretty low in energy because of the inherent energy of the boron atomic orbitals, the valence atomic orbitals. Okay, so that's all for today, and that's a way to derive the bonding molecular orbitals for diborane.